Okay, welcome. This is our diff and diff primer. Difference in differences is a great identification strategy because it is very broadly applicable to the types of questions we might ask. B, it is intuitively accessible, meaning that even if you have trouble or just don't understand the underlying statistical principles, it still makes sense what we're trying to do, or it can still make sense what we're trying to do, right? And it's also visually accessible, meaning that to an extent we can depict what is happening in figures and graphs, which is, really makes it pop, right? Even for those that understand the underlying statistical principles or understand the econometrics of what you're doing, being able to depict something in graphs and figures sells the point in a very different way, right? Like on some psychological level, we find that more persuasive if we can see in some sort of time series or graph what is going on, more so than a coefficient estimate with a bunch of stars on it, even though the same information can be captured in both ways, right? So it's a very popular strategy that we will see pretty often, or you will see pretty often throughout any type of career where you're looking at economics research, right? Empirical research. So, for our example, suppose we want to think about crime rates, and in particular, the broken windows policing strategies. So if you don't know, broken windows was more of a theory, right, developed by a political economist that went through this kind of semi-arbitrary but intuitive sequence of marginal events that aggregated up to a high crime, from a normal neighborhood becoming to a high crime neighborhood. And so there are many criticisms of that actual logical progression, but it was taken as very persuasive back in the mid 80s and throughout the 90s, throughout the 90s and into the 21st century, spurred quite a bit of law enforcement thinking and policies that were implemented. So in particular, we will think about Bill Bratton in New York City and Rudy Giuliani's tenure, which began in 1994. So what I know is that in 1994, Giuliani is elected and brings in Bill Bratton, and they impose very strict broken windows policing, which is to aggressively prosecute minor crimes in any jurisdiction, essentially. So I know that in 1994 these new policies began, and I have crime rates pre and post. I could think about, right? So for our first step in trying to identify the causal effect of broken windows policing on crime rates, I could just think about pre and post, right? So suppose that I have 4 years pre Bratton Giuliani tenure and 4 years post Bratton Giuliani tenure. And what I know is that the average crime rate across 1990 through the end of 1993 was 9,000 crimes per 100,000 citizens. And post, it was 6,000 crimes per, per 100,000 citizens. These are roughly accurate with historical data, right? Then if I am Giuliani or a proponent of broken windows policing, I could say, right, that crime fell by 3,000 crimes per 100,000 residents, or as a percent change, right, we could do negative 3,000 divided by 9,000, the baseline starting point, that's a 33% decrease in crime. Bam! Broken windows policing is amazing at at decreasing crime. Am I right or what? Or are you skeptical of this claim? And your answer, hopefully, yes. You are very skeptical, right? Thing is, if you think about it, this is very much what politicians, pundits, talking heads on TV are often doing in discussing things. They identify, that some new policy was put in place somewhere, and then they look at pre and they look at post, what the outcomes were in some sort of outcome variable. So while to me this seems ludicrous, it can be persuasive. And what we're doing in Difference and Differences, just to preview, then we'll go back through a step-by-step logic, is kind of taking this idea and then making it more persuasive, making it more reliable in order for it to be more persuasive, because this possibly is attributable to the new policy, right? In this case, broken windows policing. However, you should be skeptical because there are all sorts of other things, right, that could be explaining this decrease in crime that we have not thought of. So, for example, if your first question hopefully would be, well, were crime rates falling throughout this period, not just at the break point in 1994? And if we looked at the data, the answer would be yes, they were. Or even if they weren't falling generally across this time period, was there something else that could have explained that decrease around 1994? And just off the top of my head, right, Stephen Levitt has a paper that was in that book, Freakonomics, about how the legalization of abortion led to decreasing crime rates across the country around the early to mid 90s, right? So maybe that either explains this or explains some portion of it. Sidebar, there have been a lot of criticisms of Levitt's causal inference in that paper. And the most reasonable interpretation, in my opinion, is that it was a factor in the decrease in crime, but potentially just a minor factor in the decrease in crime in the 90s. There are other factors as well. Right, so the general principle of difference and differences is this is insufficient, but if we have a comparison point, right, a good point of comparison for, this is New York City right here, right? So maybe if I'm comparing this to Boston, and the change in crime rates in Boston, or the change in crime rates in Newark, right? Or in DC, right? If I look at how the crime rates changed in some other city that we are essentially arguing is a counterfactual for what should have been happening in New York in the absence of the new broken windows policing, that Bratton and Giuliani brought in, then I could difference those differences, right, and get a more reasonable estimate of what the actual effect was. And to which I will show real quick is sort of what is happening, right, when we look at graphs like this right, this is not actual difference in differences, but if we just focus on this area here in 94 and compare the red line, which is New York City, to LA, or compare it to Newark, right, then on a much more kind of rough level, what we're doing is a form of difference in differences, right? Does this trend seem to kind of fit with this trend, and then do they deviate after Giuliani takes office from one another? And that's kind of the rough idea of what we're going to be doing with a difference in differences strategy. Okay. Now, okay, so before we get to the actual diff illustration of making this possibly into causal inference by showing that crime rates weren't changing elsewhere in cities that we could posit are a good approximation of what would have been happening in New York City elsewise. First, let's illustrate just how directly this relates to our regression equations, right? So what I actually set up here, right, is for New York City to analyze the effect of this new policy, whatever it is really, that was implemented in 1994. I'm going to look at the average crime rate, right, Y bar, given that T, the time period, is before 1994, and Y bar, given that T is equal to or greater than 94, and the change then is Y bar T equal to or greater than 94 minus Y bar T less than 94. Right? That's exactly this pre-post analysis that we just did here. What sometimes would refer to as just a straightforward case study. Well, think about our regression equation now. Our outcome of interest is crime rates, right? So the regression equation that we would be setting up here is YT is equal to beta naught, right? Some constant intercept, plus beta 1 times post T, and just an indicator variable saying, is it after Giuliani and Bratton came into office, or is it still pre-Bratton and Giuliani? And epsilon T, an error term, right? Now, to see why these are just the betas from that equation, think about what your regression equation is actually doing, right? When we use the fitted values of these, what we are actually putting together is the expected value of y, or the mean of y, conditional on whatever variables we have in the regression equation, right? Error term becomes 0 in expectation by construction of our OLS estimators, right? So So y bar t less than 94 is just beta naught hat plus beta 1 hat times 0, right? T less than 94 is all of the years for which post was equal to 0, because T is prior to Bratton and Giuliani's tenure. So that's just beta naught hat. And for T greater than 94, it's beta naught plus beta 1. Now post is equal to 1, right? So that's beta naught plus beta 1 hat. Hat on both, that is. The hats indicate that these are the fitted values from actually estimating this OLS equation with the data for the crime rates in each of these years, and simply an indicator for whether or not we are pre or post 1994. So, right, if it wasn't immediately clear that this would be an estimate of that, we can see that now by thinking about this, right, where y bar t less than 94 is beta naught. Y bar t greater than 94 is beta naught plus beta 1, all hatted, of course. And so the difference post minus pre, side note, my brain will not allow me to put pre after post here, but when we take the difference, it's always going to be post minus pre, right, in order to get how did crime rates actually change going into the post period. So that's beta naught hat minus beta 1 hat, or plus beta 1 hat minus beta naught hat, right, which is just beta 1 hat. Right? So this is just taking a very, very, very simple regression equation and extrapolating the beta 1 hat that we would get from that. Now, as I'm sure you are clamoring at your computer, right, this is not a good estimation, right, because it doesn't even account for time trends, right, which we would possibly expect here. And so once we can think of this in a regression equation, it is pretty straightforward to expand our regression equation, right? Just add another term that has time as an actual variable, and that is imposing a linear time trend on my estimates of the crime rate, right? Fundamentally, this is still estimating the break in the fitted values, right? The break in the conditional means between the pre and the post period. It's just now we are accounting for a linear trend in crime rates over the entire period, right? Now, a couple of things that we might do to expand this, right, is first of all, a linear trend may be far too restrictive, right? And so if you want quadratic or cubic, we can just add those terms in here, right? I think there's some curvature up to the time trend of crime, then I could just add beta 3 t squared plus epsilon t. And because this takes essentially zero effort, well, not zero, but very close to zero effort to re-estimate your model in estimating this equation with any particular set of data that I have, I would probably add a third cubic term, right, as well, to add even more flexibility to the time trend that I'm fitting, and see if it changes anything, even if this is my preferred specification based on my view of the data. Now, so all of that fundamentally doesn't change the fact that this beta 1 hat is still the estimate of the change in expected crime rates in the pre and post period. It's just, in this case, right, it would be conditional on more factors, right? Okay. Okay, so one more comment on adapting our regression equations before we move back to adding our second difference, right, is in addition, or rather than the flexible time trend that we just did there, right, you might also just think that the implementation of our new policy may have changed the trend over time. Not that there was, maybe it's reasonable that it was linear and that it is linear post, but that the linear relationship changed after the new policy, right? And so this regression equation is imposing that the linear relationship with time is the same pre and post implementation of the policy. So if what I'm positing, right, is that we had this policy come into effect, and this is time, this is y, and what I think is that there was some linear time trend, and then not only was there some shift in the values of y, but after that the time trend changed. Say it went to roughly flat, then I want to allow for that in my regression equation. So that's what an author has in mind if they do something like this, right? So I've still got my post variable. I've still got beta 2 times the time, but then I add time, which is just counting which year we're in, times post t. Right, so that's going to mean that once we pass 1994, not only does beta 1 get added to the constant in the fitted estimation, right? But the way that crime rates change over time also gets adjusted by beta 3 because post becomes equal to 1. So if that's not totally fitting or connecting, right, think on it for a little while, because, right, this kind of intuitive connection between what our regression equation is doing and what, like, the ways that we can visualize that is very helpful in understanding and interpreting regressions properly. Okay, so now just want to re-emphasize one more time, right, that adding this additional variable in here fundamentally didn't change that beta 1 is the estimated difference in the expected crime rates across these time periods. This equation relative to that equation is just accounting for that there may be a time trend. Right, so again, y and t. So if, as what we suggested, there is a downward time trend prior to the policy, and then we do this, and then resume that same time trend, right? What this equation would be doing is fitting that apparent shift right there, right, to the beta 1, and then approximating that linear decrease in crime over time to this beta 2. Whereas this original equation, right, excuse me, is just taking the average crime rate over the entire pre-period, right, and taking the average crime rate over the entire post-period, and taking the difference between them, right, would be this estimated beta 1. Right, so by fitting a time trend to this, I would get a smaller estimate of beta 1 hat, because I'm not attributing the overall decrease in crime over time to that treatment in period 94. Okay. So back over here. Suppose we do buy the argument that Newark, I'm not so sure if that's how you're supposed to abbreviate Newark, but we're going to go with it, that Newark is a good counterfactual for New York City. That is, this broken windows policing was not implemented in Newark, and crime rates in Newark, or more specifically, changes in crime rates in Newark, are a good approximation for what would have been happening in New York City, right? So, looking at that figure that I showed for a moment earlier, I think Newark had approximate averages of 15,000 and 13,000 over the relevant periods. Right? So all these numbers are very approximately based on that figure that I showed you. And so the change in Newark's crime rate is 13,000 minus 15,000. So that's 2,000, negative 2,000, right? Decreased by 2,000. General principle here, right, or the actual principle that we're going with here, right, is that if this untreated group is a reasonable counterfactual for what would have been happening in the treated group, then we can take this and difference it from that to get the actual decrease in crime, right? And so that would be negative 3,000 minus negative 2,000, or plus 2,000, meaning the net effect be negative 1,000, right? So basically, eyeballing that that figure, I could make a much more reasonable claim, still, right, if we think about it, subject to quite a bit of criticism, but a much more reasonable claim that the broken windows policing was responsible for a more modest decrease in crime in New York City, right? And part of why, right, subject to quite a bit of criticism is in addition to any number of other omitted variables that we might posit, the Newark crime rates may not be a great counterfactual for New York City crime rates, right? In fact, there may be an explicit endogeneity problem between Newark and New York City, right? That maybe this policing policy in New York City actually just displaced some crime into Newark, and therefore Newark didn't see the same amount of decreasing crime rate as New York City did, and the true estimate is unclear, completely unclear. Now, this is the basic idea with just two different cities, right? We could expand this idea, and this is often what we are doing in a difference in differences strategy, to many different treated cities and many different untreated cities, right? Or to many different treated smaller units within a treated city and many different untreated smaller units within an untreated city. So the example of that would be a classic example of a difference in differences that, I forget what the two states were. We'll pretend that it was Vermont and New Hampshire, even though I don't think that's true. You have a number of different businesses that are right on either side of a state line, and one state implements an increase in their minimum wage. One state implements a decrease in, or an increase in their minimum wage, the other state does not. Then the change in employment, right, for those businesses on the side that increased the minimum wage, right, relative to the change of employment for those many businesses right on the other side of the state line, that would be a difference in differences comparison of many different businesses that were all treated on, say, the Vermont side of the line and all untreated on the New Hampshire side of the line. Okay. How does that then transfer into an actual regression equation like this, right? So note that previously, when we were just thinking about New York, it was always New York, so it was just what year were we in New York City. Now we would want to have I to indicate whether we are thinking, which unit we are thinking about. In this case, is it New York City or Newark? Or if this is policy is more broadly applied, which of those cities is it and what year is it? And then we would have our beta naught plus beta 1 post still. And post is still only dependent upon the time period. But we would also have, I'm going to use it X because writing out treat is a problem for how much space I have here. But think of X as equal to treat. Right, so this is an indicator for whether or not it's pre or post implementation of the new policy, and XI is an indicator for whether that city is among those that were treated by the new policy. Note that this is always equal to 1 for any city that is in the treatment group, right? In this case, it would just be for New York City, regardless of what period we're in, right? So for New York, beta 2 is the fitted value of beta 2 is always included in their conditional mean. And post is equal to 1 for all cities in all of the post-treatment periods, regardless of whether or not they were a treated city. And then we have beta 3, which is going to be post t times xi. Right, so now this over here is just the interaction of, I'm going to underline it so that it's distinguishable, or slightly more distinguishable at least, right? The interaction of that post indicator and the treated indicator, right? So this is equal to 0, except when both of these are equal to 1, right? So only for a city that is treated and during the periods after which the treatment has occurred, as in the policy has been implemented, right? Then we have 1 times 1, and the fitted value of beta 3 is active, so to speak. Okay, so we're getting there, right? What we have here now is essentially the most basic form of a difference in differences estimating equation, with the addition of this term that I left in there to kind of remind us that we can be controlling for a time trend at the same time as this. And in many cases, right? You should be controlling for a time trend. And in fact, should probably be controlling a little more flexibly for the time trends. That is also potentially a reminder, which we'll come back to in a second, that we could control for other factors as well, not just time trends. But let's come back over here now and illustrate for ourselves that this is that beta 3 hat estimated, right? So doing the exact same thing, really, as we did previously. Just recognizing now that we, instead of just yt, we have yit, and New York City is the I for which xi is equal to 1, and Newark, is the city for which I is equal to 0, right? Because it was not treated. So then the expected crime rate in New York City pre-1994 is when post will be equal to 0, but x is equal to 1, right? And we're going to ignore this term over here. So we're imagining this equation without that term, essentially. So post is equal to 0, meaning that here and here the variable is 0, but xi is equal to 1, because New York City is among the treated cities, the only treated city in our thought experiment here. So that's beta naught hat plus beta 2 hat, right? And in the post period for New York City, now post is equal to 1, x is equal to 1, so post times x is equal to 1, and the expected value of this, we'll just illustrate it real quick, right? Y bar, we'll say 1 is for New York City, and t greater than 94. All right, so New York City after during or after 1994 is beta hat naught plus beta hat 1 times post is equal to 1 plus beta 2 hat times x is equal to 1 plus beta 3 hat times post is 1 and x is 1. Right, so beta naught plus beta 1 plus beta 2 plus beta 3, all of them are, you might say, active in estimating this expected value here. Now, when we move down to Newark, right, in any time period, pre or post, for Newark, x is equal to 0 because Newark was not treated, right? Therefore, beta 2 is always multiplied by 0, and beta 3 is always multiplied by 0 because the x is 0 regardless of whether it's pre or post, right? So this is just going to be beta naught hat and beta 1, or excuse me, beta naught plus beta 1 hat. Let's give myself a tiny bit more space here to do the changes. So the delta then, or the difference for each of them is post minus pre, right? So post for New York City is all 4 coefficients minus the beta naught and the beta 2. So that's beta 1 hat plus beta 3 hat. And for Newark, it is beta 1 plus beta naught minus beta naught. So that's just beta 1 hat. The difference in the differences is our beta 3 hat. All right, so this estimation here is just an extremely simple regression equation, right? Estimate of beta 3 in this equation. And this particular equation is slightly more complex than this because it has added a time trend by including beta 4. Right, so that would be accounting for those time differences, but the beta 3 would still be the shift in the expected values of y that occurs right when the policy is implemented for the treated group relative to the untreated group. Right, so beta 3, as we add more controls to make our expected values conditional on more things, beta 3 is still the shift in the expected values of our outcome variable relative to the untreated group. And so even though, right, we can't exactly put the values into a table like this when we control for more factors or simplify it into actual coefficient estimates like this, it is still the beta 3 or whatever coefficient, in the ordering of our actual estimating equation, whatever coefficient is attached to the interaction of treatment group and post-treatment, that coefficient is still the difference in differences estimate. And that's an important thing to keep in mind here, right? Because the way that in application, we're going to end up setting up difference in differences equations is going to vary a lot because So for example, suppose I include fixed effects in this regression. If there are many different cities in my sample, right? It's not just New York and Newark. We have all of the major cities in the U.S. and 20 or 10 of them implemented a broken windows policing program, right? Then I might want to include a city fixed effect, right? For each of those cities have their own fixed effect. And that is fine. I can add that fixed effect to this equation, right? Just a gamma I or something like that. But what that's going to do is invalidate, or not invalidate, but it's going to be perfectly multicollinear with this treatment indicator right here, right? Because for each of those cities that now has a dummy variable indicating which city it is, either they have a 1 for treatment or they have a 0 for treatment, and it never changes based on the time period, and therefore this term is just going to be unnecessary, right? In fact, if you ran that type of equation, right, with a treatment indicator and with individual fixed effects, Stata would just drop your treatment indicator, right? But it wouldn't drop this one because that is interacted with something that is time varying. So the individual fixed effect won't subsume the marginal effects of this on your dependent variable. Okay. Okay, so we've got, hopefully, the idea of not just what difference in differences is trying to do, why it's doing it, and what the comparison that it's making is, but also the regression equation version of that identification strategy, right? But as I alluded to earlier, and I can just imagine that you are like trying to raise your hand right now and ask, is what makes a good counterfactual, right? What if it is still very questionable whether this comparison that we've made here has given us a reasonable estimation of the real causal effect of broken windows policing in New York City on their crime rates. Why is it that I might be concerned about Newark, or why might I be very convinced by Newark? And so authors will go through all sorts of different sort of streams of logic and thinking to convince you of this, but essentially, right, it often will come down to either just an intuitive argument. For example, in that minimum wage case that I was talking about earlier, the fact that we are looking at businesses right on either side of a geographical border, and it is a porous border where individuals can cross back and forth over the border pretty much at will, is intuitively suggestive of, right, these businesses are fundamentally subject to the same economic pressures, the same demand base, and et cetera, except for the laws that apply on this side of the border and the laws that apply on this side of the border. So in order to argue that that was a good comparison, all I really needed to do was make the case that this was the only real regulatory law pertaining to these businesses that changed over the time period of that difference in differences comparison, right? Beyond that, there's no real reason to expect that New Hampshire businesses are in any fundamental way that different from Vermont businesses, and more importantly, right, because it doesn't actually matter if at baseline there are some differences between the policy, the treated group and the comparison group. What matters is that the way that the outcome variable, in this case employment, changes over time are fundamentally the same, that there's no reason to expect differences in that. So in this case, right, that would be intuitively, maybe Newark is a good comparison because it's so close to New York City, and so crime trends might be similar because of that. On the other hand, maybe Newark is not a great counterfactual because crime in New York can affect crime in Newark and vice versa, right? And so there's an endogeneity issue here. And so maybe I would argue that that Boston or any city you want to think of, Chicago or whatever, could be a better comparison group, or that none of them are very similar to New York because New York is New York. Or I might want a sort of data-driven approach to saying, look, you can throw whatever you want at me about why New York is so unique, but if I can show you that crime in New York is highly correlated with the city that I'm using as a counterfactual, then your argument is losing water quickly, right? So that is what I'm just going to throw this right in the middle here. Oops, spelling things wrong. I think that's right. Parallel trends assumption is one of the things that we look for, right? As a persuasive argument for having a good counterfactual. And let's look back at this figure, right? The idea is if prior to our policy implementation, if the changes in the outcome variable are matched across the two across the treated group and the counterfactual group, then that's pretty persuasive argument that one is a good counterfactual for the other, right? In this case, Newark is the blue line up here, and New York City is the red line down here. Now, the trends are parallel to the extent that each one is decreasing in each period, right? However, I would kind of note that there seems to be, like this giant decrease in between 1990 and 91, and then much smaller decreases, and these kind of steady-ish decreases over here suggest more volatility up here. And I could note that the largest decrease in New York City occurs between 91 and 92, as opposed to the 90 and 91 up here. So they do have the similar downward trends over this period, but they're not strictly parallel to one another, right? I would be much more convinced if I had a city here that also had a small decrease in crime in each period, and the largest decrease was in this same year as it was for New York City, right? And even more convinced, right, if I could expand this back through 1980, right, add another 10 years and show that my chosen city, right, has almost the same changes in crime rates over that much longer time period, right? That's just more evidence suggesting that New York City and that city are subject to the same sort of pressures on our outcome variable over time. In this case, right, this is a pretty weak fit of parallel trends. Side note, though, by and large, right, I don't care about the fact that the baseline is higher for Newark, right, relative to New York City. That doesn't actually matter to me, right, other than thinking kind of, there's no rule on this, but thinking about the variable that we're measuring, it may suggest, right, if I have a higher baseline, that I have higher volatility in that variable, right? So the unit changes might be greater if the average crime rates are much higher, right? So the average may increase or decrease more so than for a city with lower crime rates. And in that case, what that would imply is maybe I need to rethink the specification of my model, right? That so suppose here that Newark has this same sort of trend as New York City, but all of the changes are larger, right? Where this appears to be, like a, I don't know, maybe a change of 200 or 300 in the crime rate, and this is a decrease of around 500, and this is a decrease of 200, right? If all of those were doubled in the change in the Newark crime rate, but it matched, as in it's about a 600 decrease of 600 crimes in the first shift, a decrease of 1,000 crimes in the second shift, and a decrease of 400 crimes in the third shift, then that would be a nice almost identical parallel trend that's scaled up by the factor of the baseline, right? And so I could just quite simply just change my model to be a log of yt, right? Because those are percent changes that match up with one another. Then perhaps this would be a better way to match the crime rate trends in my treated group to the crime rate trends in my counterfactual group. But generally speaking, right, parallel trends does not, right, in order for parallel trends to be persuasive, it does not require that the trends actually lay on top of one another, right, that they have the same baseline crime rates or the same baseline employment rates or the same baseline profits, right? The comparison group need only be subject to the same or similar changes in the outcome variable over time in order to persuade us that those changes are a good approximation for the changes we might have expected in our treated group after the policy was implemented. All right, so that's our parallel trends assumption that when possible, the author should, and so you should look for in a paper, should present a figure kind of like this, hopefully more refined than this, illustrating their parallel trends assumption. On occasion, with some of the kind of more challenging applications of difference and differences, right? It may not be possible to depict the parallel trends assumption like this, and so instead we might do some kind of statistical test to make the argument that despite the fact that we have to control for additional variables and in our comparisons, and therefore can't construct a clear parallel trends figure, we could still test some sort of assumptions to show that there's a good match between the pre-treatment trends among the treated and untreated groups. Excuse me. Okay, so one last comment about finding good counterfactuals for this difference and differences type of thing is sometimes, particularly when you think about kind of city comparisons like this, it is difficult to find, right? Sometimes it's straight up impossible to find a suitable counterfactual, right? That every city we compare with New York has some concerns about it, right? And so one of the strategies that we will probably see over the coming weeks is to accept that there are problems with all of the choices that I have available. Maybe I do estimate a difference in differences model with various different counterfactuals for my treated group, but there's still some concern, and so another strategy to essentially do the same thing, is to construct a synthetic, what's known as a synthetic control. So we can construct a synthetic New York City by taking the crime rates in Newark and in Boston and in Chicago and in LA and in Denver, right? Any set of options, right? And taking a weighted average of all of them, right? To kind of create a good parallel trends fit, right? So there's an algorithm that we use, right? That's in a data package and widely accepted as well, somewhat widely accepted as an effective method, right? To get the best fit for New York City on those pre-periods and potentially on a set of additional control variables, right? To construct a synthetic New York and then do a difference in differences just like this, right? So it's a very data-driven attempt to get nice parallel trends between New York and essentially a fictional counterfactual group that has been constructed from the data, a weighted average of the data of a bunch of different potential counterfactuals. And so that is something that we will likely see. And also want to illustrate, right, this is a common adaptation that we will probably see, right? The form that you will very often see in a difference in differences estimation in a paper, right, is going to have these dual fixed effects, right? We're going to have individual fixed effects and time fixed effects, which we need a nice broad and long panel to do, meaning we need to have many different individual cities or individual firms or individuals in the data, right? And also many different time periods. And if we have a sufficient number of both of those, then you could have both your individual fixed effects and a time fixed effect for every time period rather than a time trend, right? Which is just a much more flexible controlling for changes over time. And those two fixed effects are going to subsume the need for post or treat to be its own term in this regression, right? So we're just going to have beta naught plus beta 1 times the interaction of post and treat, right? And then have those fixed effects that will account for, whether or not a particular city was always among those that were going to be treated, and this will account for whether or not there were shifts for all cities at the time that the treatment came into effect, shifts in the crime rate in this case, right? And then this term here, right, I've included, is a set of potential controls, and indicated that this is a vector, so it's not just a single control variable. There are, this is really a bunch of additional terms that we are including in the regression, with each of them having their own coefficient associated with them. And note that we subscript that with IT, because with these fixed effects, the only controls that have any meaning are variables that vary between cities and over time, right? And so I should correct that. It's not that the only variables that have any meaning, but the only variables that add any additional variation to this that we could capture their effect on Y would be things that vary between cities and over time. And so this is just a stylistic thing in most papers, right? Because we're not actually concerned about the additional things that we're controlling for, what exactly they are and what their marginal effect is. We're just accounting for them because we're concerned that if we don't, we may have an omitted variable problem, right? So that will often be lumped into a vector as kind of like, and then we'll, kind of as a side note, describe what variables might be included in that vector. Again, right, this is making our expected values of y conditional on additional factors. And fundamentally, right, if we are very persuaded by parallel trends, the parallel trends assumption in our difference in differences strategy, and if it's a good, just clean difference in differences strategy, we really shouldn't need to control for additional variables, right? Because the policy implementation was unexpected. The control group is a good counterfactual for what would be going on in the treated cities. Then there's no reason to expect that any of these would be correlated both with this and with y. But sometimes there are still, residual questions. Sometimes it is just helps reinforce the reliability of this estimate if we have the same estimated coefficient here, regardless of whether you include additional controls or not. So we'll see this in the estimating equation often. And we should recognize that that we're not particularly concerned with the coefficients associated with those things. It is potentially a concern with the strategy if the estimated value of this beta 1, that is the coefficient we're interested in here, right? Because we reorganize this equation, it's no longer beta 3 hat, it's beta 1 hat that is the coefficient of interest. But if that estimate changes considerably when the authors change what variables are included in this set of controls, then that's a potential cause for concern. Okay. That concludes our difference in differences primer. We will take a moment at the start of our Friday discussion if you have questions specifically about this, or you can come see me during office hours.